The next relationship we're going to look at is double angle formulas. Sometimes people call them the 2 theta formulas, but I prefer to say double angles because who's to say you're doubling theta? You might be doubling something else. So sine 2 theta. So to create it, I can rewrite 2 theta as theta plus theta and then use the formula that we've seen. So sine, cos, cos, sine. If it's the sine, it's the sine. And we notice, hey, look, we've got the same thing. So actually, that's just 2 sine theta cos theta. Cosine's a little bit more interesting. So I do the same idea, theta plus theta, but look what happens now. We get cos cos, sine sine. If it's not the sine, it's not the sine. But we get cos squared minus sine squared. However, if I want to write it in terms of just one of those, I can change the sine squared to 1 minus cos squared. And then tidying that up, we get 2 cos squared minus 1. Or, if I want it in terms of sine squared, I could change the cos squared to 1 minus sine squared. And so we have 3 different ways we could go and find cos 2 theta. So I just guess it depends on what information you've been given as to which one you would use. And tan plus tan on 1 minus tan tan. But then the top of the fraction becomes 2 tan theta, and the bottom is 1 minus tan squared theta. So they are our double angle formulas. Let's summarise those again. Sine 2 theta, 2 sine theta cos theta. Cos 2 theta, cos squared minus sine squared, or 2 cos squared minus 1. Now that's interesting. If you rearrange this, look what you get. You get cos squared theta equals a half of 1 plus cos 2 theta. That's going to become very useful, certainly next year when we're dealing with integration of such functions. And next year, when we do come to integrate such functions, I'm going to go, hey, remember last year when I said, hey, this will be really useful, and then you all will sit there and go, no. Remember it. It's going to be very useful. It's going to be very useful. And then the other one, 1 minus 2 sine squared, and we make sine squared the subject. They're very similar, you'll notice. But cos squared theta is 1 plus cos 2 theta, and sine squared theta is 1 minus cos 2 theta. So those ways of rearranging the 2 theta, the cos 2 theta, as I say, will become very handy. And our tan 2 theta, 2 tan theta on 1 minus tan squared theta. Well, let's do a few examples. They've told me cos theta is 2/3. They want us to go and find tan 2 theta. So I say the boring way of doing it would be to, let's go and work out what theta is, double it, find the tan of that and hope it turns into something I can read off the calculator and recognise. I find it a lot easier, just go to the triangle. So I know cos theta is 2/3. So the other side's root 5. So tan 2 theta, substituting in, 2 tan theta on 1 minus tan squared theta. And I get, eventually, minus 4 root 5. Find the exact value of sine, and I've done it in radians this time, 5 pi on 12 cos 5 pi on 12. Well, that's very close to one of the relationships we just looked at. But we had 2 sine theta cos theta, not 1 sine theta cos theta. Well, that's easy enough. I could rewrite the sine theta cos theta as a half of 2 sine theta cos theta. And the 2 sine theta cos theta is sine 2 theta. Theta in our case is 5 pi on 12. So double it, I get 10 pi on 12, which is 5 pi on 6. 5 pi on 6, that's one of our exact ones, isn't it? Where's that? That's in which quadrant? 5 pi on 6. Who's good on their radians? Second quadrant is correct. What is the equivalent acute angle we're looking for? 30 is correct. Sine 30 is, of course, 1/2. So we get half times a half, 1/4. 1/4. Cos theta is 2/3. Find the exact value of sine half theta. This is why I say thinking of them as double angles is probably better, because theta is double half theta. So there's the relationship. So really it's like saying cos 2 theta is 2/3. Find sine theta. Well, I'm going to use the rearrangement of the sine squared one. So sine squared theta is a half of 1 minus cos 2 theta. Now let's rearrange that just to make it a little bit more obvious. So what I'm really saying is sine squared theta on 2 would be a half of 1 minus cos theta. I can substitute in what they've given me for cos theta. So I now know it's 1/6. Well, that's sine squared plus or minus 1 on root 6. Can I eliminate either of those? Without any more information, we can't discount the plus or minus. We'd have to leave that as plus or minus. Or let's prove a trig identity. The square root of 1 minus cos 2x over 1 plus cos 2x is the same as tan x. I'm going to start with the left-hand side. I think would be the most logical place to start. But of course, with cos 2x, I've got 3 choices of what I substitute in. And this is where we have a look at what we're trying to prove. I'm trying to prove tan x. So if I'm going to substitute in for cos 2x, what would I like on the top of the fraction if I want to end up with tan x? So which of the 3 different ones would I use for cos 2x for the top of the fraction? Right. Now the bottom of the fraction, I'd like to end up with cosine. So for the bottom cos 2x, I'll use the 2 cos squared. Okay. And it works out quite nicely because of the 1's. So 1 minus 1 disappears, 1 minus 1 disappears. So I've ended up with 2 sine squared on 2 cos squared. 2's cancel, sine squared on cos squared. Find the square root of sine squared on cos squared. Sine on cos. Oh, well, I actually did the tan squared first. Square root of tan squared, and there's our tan. So if you're unsure of what to substitute in, have a look at the answer if they've given it to you, and that can give you clues as to which way to go. Here's one from 1996. Wow, long time ago. Sine 3 theta on sine theta minus cos 3 theta on cos theta. We have to prove it's equal to 2. A lot of people wasted a lot of time on this particular question. I do remember it. Because people saw the sine 3 theta and they thought, oh, I've got to create a formula for sine 3 theta just like we got for 2 theta. And so they went and said, oh, well, sine 3 theta, that's the same as 2 theta plus theta. And so ended up with sine cos, cos sine. So it was sine 2 theta, cos theta, and so on. And then said, oh, now the sine 2 theta, I'll make that 2 sine theta, cos theta. It works, but it's a lot of work. There's a much quicker way of doing it. Here's the left-hand side. If I just turn that into an algebraic fraction, the denominator is sine theta, cos theta. The top becomes sine 3 theta, cos theta. Minus cos 3 theta, sine theta. But look at the pattern. Sine, cos, cos, sine. So I can rewrite the top as sine 3 theta minus theta. And I've also then multiplied top and bottom by 2 as well. And look what happens. The bottom, 2 sine theta, cos theta, sine 2 theta, and 3 theta minus theta, 2 theta. So we get 2 sine 2 theta on sine 2 theta, which is 2. Much, much quicker than the other idea, which, as I say, a lot of people tried to do that particular year. And it did work, but obviously took up a lot more time. Here's an even older one, 1994. 2 tan A on 1 plus tan squared A. We're going to show this one is sine of 2A. So do I start with the left or start with the right? I mean, the right-hand side, I could change that to 2 sine A cos A. What would I do after that? Not sure. Maybe I'll start with the left. 2 tan A on 1 plus tan squared. Actually, that doesn't help me as much as I originally thought, because I was looking for 2 tan A on 1 minus tan squared a. That would have helped me because I could have turned that into tan 2a. So what did I do? Okay. Whenever I get stuck with tan and I know the answer involves sine or cos, turn all the tans into sine and cos and let's see what happens. So 2 sine a on cos a and 1 plus sine squared on cos squared. I've now got fraction on fraction. Let's multiply everything by cos squared a and get rid of those fractions on fractions. Look what happens. Comes out quite nicely. Top of the fraction becomes 2 sine a cos a. There's my sine 2a. Bottom of the fraction, cos squared plus sine squared, which is, of course, 1. We got it. There it is. Sine 2a on 1, sine 2a. Alrighty, let's play with some of those. So now we go to book 2.